Hey, thanks a lot, Martin, and thanks everyone for waking up early and showing up to my talk. I'm excited to talk today about Spark 2.0, and more generally, I'm going to talk about sort of the development of APIs in Spark as we learned from from the first version of it. So as I'll talk about, Spark started out with this kind of crazy idea of just taking this functional language Scala and making all the functions run on a cluster and making some of the distribution transparent in that way. And I'll talk about what worked well with that and what didn't, and some of the new things we've been doing in it. So what is Apache Spark? It's a general purpose processing engine for clusters. So by general, I mean it tries to support a wide variety of workloads. And it does this by basically extending Google's MapReduce model to support more types of applications. In particular, it adds these primitives for data sharing that let it do iterative things and streaming and all kinds of things that need to maintain state as they run. The engine provides all the things you'd expect in this kind of engine, distribution of work, scheduling, load balancing, fault tolerance, and so on. Increasingly, Spark is also not just an engine, but a collection of APIs and libraries that are all designed to work well together. So it has the core sort of functional API. You can use it in different languages, including, of course, Scala, which is what it started out with. And it also has these 4 standard libraries on top for SQL, streaming, machine learning, and graph processing. And these are all designed to work well together so you can combine them in a program. And Spark has gone into a very, pretty large open source community. This is a picture of just the meetups of it around the world that are active like right now. If you look at just the commit activity on the project, patches per month, bugs open, things like that, it's the most active of the open source big data projects right now. It's been that way for probably like around 2 years. It's used in a variety of places. We counted over 1,000 deployments of it, over 1,000 organizations. The largest cluster that people have talked about publicly is around 8,000 nodes. So these are some of the companies that use it. Okay, so what am I going to have in this talk? I'm going to start with kind of the original goals for the project, the original vision, and then how did the vision hold up. And then I'll talk about probably sort of the most significant change or extension of Spark APIs, which is structured APIs. There are these 2 new APIs, new in the last year, called DataFrames and Datasets, that try to address some challenges in the original one. I'll talk about optimizing underneath these structures APIs, some cool things we can do there, and then about some of the next steps in this direction in Spark 2.0. Okay. Cool. So what's the original Spark vision? So basically, we had 2 goals for the project. First goal is we wanted to have a unified engine for big data processing that supports the different types of workloads. So when you do big data processing, you're going to run a whole bunch of batch jobs, but a lot of it is also interactive, exploring the data. A lot of it is iterative algorithms that go over the data many times. And eventually, if something works well, maybe you want to turn it into a streaming sort of continuous job. And before Spark, a lot of these required separate engines basically to build, which was very time-consuming for developers. So we wanted a unified engine. The second goal we had is that we wanted this concise language integrated API that looks kind of like working with local collections of data. And we did this through this functional programming API in Scala, Java, and Python. Okay, so just what's the motivation? So when you look at cluster computing engines, the first one was MapReduce, and actually a big deal about MapReduce, if you go back and read the presentations on it or the papers or and so on, is how general it was. Google said, hey, we built this thing once, and then we were able to run all these different applications on top of it. Reporting every night, web indexing, machine learning, all this kind of stuff. So generality was super important. But after this came out, there were a whole bunch of new workloads that required slightly different things from the engine. And people ended up building a whole bunch of specialized systems. So even in Google, they built Pregel, which is a graph processing system, Dremel, which is an interactive SQL one. And outside Google, mostly in the Apache open source community, there were all these other systems like Giraffe and Impala and Storm that are specialized for different workloads. And these, having these is great because you can do more workloads, but it's hard to manage, tune, and deploy all of this. All the hard work, if you've ever done it, of managing something like Hadoop, now you get to do it over and over again for each of these applications. And even more than that, even if you can install them and stuff, it's hard to combine them into pipelines. So a real application will usually use a mix of these things. You don't just get like a graph handed to you or a bunch of vectors for machine learning. You have a pipeline that transforms data and maybe runs several different algorithms. And now there are different engines with their own programming models and data formats and so on. So the question was, can we go back to a more general engine and still capture these workloads? And that's what we wanted to do with Spark, to design a unified engine for these. Okay, so that's the unification part. For the Concise API, the motivation is pretty simple. A lot of data analysis is very exploratory or interactive. You don't want to spend a lot of time writing these jobs. So Spark introduced this API called Resilient Distributed Datasets, or RDDs, which are just distributed collections. If you work with Scala collections, you already know a lot of what it takes to work with RDDs. So they're distributed collections with a simple sort of functional API. So as a really simple example, in Spark you can create something like a text file, which is an RDD of strings. It's a distributed collection of strings in some distributed file system. You can do things like maps on it. So here we're going to turn it into a bunch of point objects. Now we get a collection of points. You can do filters, you can do counts, group bys, joins, all kinds of operations like that. And the API, I guess I should say, the API is also lazily evaluated. So it doesn't run these things until you call a special operation that produces an output. And that means that it has some chance to optimize the job based on what you're doing at the end. So in this case, like, when we're doing a map and then a count, it's never going to save these intermediate results. It just counts the ones that pass the filter. So it does a little bit of optimization underneath that as well. Okay, so that's kind of the basic Spark. So how did the vision actually hold up? Are people using it in the way we kind of intended? Generally, it worked pretty well. Users really like this unification aspect. Most users use a mix of these libraries and do applications that combine different things, which is really cool to see. The functional API and basically just building it around Scala functions and objects did cause some challenges, and these are the ones that I'm going to talk about now. So on the unification side, here's again a picture of the libraries built on Spark. We built these all kind of after the core engine came out, and we were able to capture a whole bunch of workloads, SQL queries, streaming, machine learning, and graphs, and to run them on the same API involving RDDs. And together, they're currently the largest sort of integrated standard library for big data. And when you look at how people use them, people actually use a good mixture of these things. So this is a graph from a survey we did last year. So you can see each of these libraries on top of the core API is used by at least 50% of the organizations in this survey. And also 75% of them use more than one component. So basically two of the libraries together. And we're excited to see this because this is one of the things we wanted to enable is to let you mix together these processing types. The applications people use them for are also interesting. There's a whole range of those as well, which is nice to see because we wanted to have something pretty general. So the most common things are data warehousing and business intelligence, which means basically computing reports, kind of simple like statistical aggregations or data cubes or things like that. But we also see things like recommendation engines, log processing, user-facing services. So this is an application where like a user is interacting with a UI and it's running Spark on the back end as they interact with it. I guess this is misspelled, but fraud detection and security. So these are also some of the things people are doing. Okay, so that's kind of the unification side. So what about the kind of the challenge, the functional API? Nothing wrong here, by the way, with the idea of functional programming, just kind of the level of visibility we have into user programs is the problem. So basically, the API looks high level. Like I showed you this code where we're just running map on a distributed file, and we automatically send the work to all the nodes and split it up across a cluster and stuff. But it actually hides a lot of the semantics of the computation from the engine. And that makes it hard for the engine to automatically optimize stuff, and it means the programmer, needs to be pretty careful to get it to run efficiently. So the functions that we see, like the lambda function I pass to a map, is just an arbitrary block of Java code. It's really hard to figure out what it's trying to do. And the data is also stored in arbitrary Java objects, so there's not a lot of room to optimize how it's stored and how it's sent across the network. And kind of the end result of this is users can mix the APIs in suboptimal ways. So as a little kind of quiz on that, basically I'm curious if people can guess which of the API calls in Spark causes the most sort of support tickets or like questions on the mailing list. Some of these I use more often than others, but I'm wondering if people have some idea. Which one? Join? That's a good guess, yeah. Join is definitely tricky, but it's actually not done that often, so. Other ones? Yeah, so someone said, so it's actually, yeah, it's actually grouped by key. This is an innocuous seeming operation that's unfortunately pretty tricky just because of the way it's set up. So this is actually the one that causes the most problems. And the reason why is because, basically because group by key is set up to return a sequence, because that's kind of how we're representing. We thought it was most natural to represent groups in Scala, basically. So here's an example of a problem. This is just gonna be a use of word count, basically. So we have a file, say it's a bunch of words, and we map it to pairs, word, comma, one. That's fine. And then we group them by key. And then for each list of ones, we compute its sum. So that looks like a reasonable way to do word count maybe. And if you were working with a small data set, like 1,000 words, 1,000,000 words on your laptop, that's okay. But the problem is the API of these things. So the API of group by key is that it returns an RDD containing sequences of the value, like sequence of int in this case. So you have, so that means all the ones that we sent across the network, even though we're just trying to add them at the end, first they get put into this giant vector of ones, which needs to be sitting in memory because the API is like, we're just gonna give you a sequence of these and then you're gonna run weird arbitrary Java code on it and we don't know what it's doing. So like it better actually be a sequence. And then later, well, as soon as we did all the work to create a giant sequence of ones, you're just going to sum them. So, looking at this, it would have been really nice if we somehow knew that you're going to sum them and not had to actually materialize these guys in memory. Now, the solution in Spark is, of course, you don't use group by key here. There's a different operation called reduce by key. But for users, especially new users or people not from a big data background, it can be pretty confusing because the operations look pretty innocuous. Also, maybe you used to group by from a database, and all of a sudden the combination of them isn't great. And there's not much we can do in the engine because this guy's signature is to return a sequence or an iterable, actually, I should say. But even with that, we don't know what you're gonna do later. Like you might be doing some, but you might also be doing some totally weird thing that requires a real sequence. Okay, so this is what I mean by kind of the object-oriented functional API being a problem. And then a second problem with it is that the API is in terms of Java objects, and although we can play tricks like when we send them over the network or even when we store them in memory, we can serialize them. Most of the time when you're working with Java objects, they just have a lot of space overhead. And for an in-memory computing framework in particular, that can be a a problem. So even if you have a simple object in Java, like here we've got a user class with a name and a bunch of ints, a bunch of friend IDs. If you look in the object, most of the memory allocated for it is actually kind of overhead. So each Java object has a header that's usually around 16 bytes. And then in this case, the user is going to have pointers to a string and an int array. Each of those will have a header. And then the int array has its length, and then it has a bunch of data. And then the string itself is an object with a pointer to a char array. And then the char array, also has a length and a bunch of data and maybe some padding to make it, kind of aligned to a reasonable size. So when you look at it, probably like 2/3 of the space in here is kind of wasted. And this is typical in a lot of common data structures. Again, it's fine when you work with like a few thousand of them in your laptop, but it's not that great when you're trying to work with lots of them. Okay, so basically these were kind of the two problems. But overall, people do like the kind of language integrated API, so we don't want to step away from that either. So how are we solving this? So basically, to address these problems, we introduced two new APIs in Spark, DataFrames and Datasets that are structured APIs. I'll talk about that, but they put a few more restrictions on the data so that you can understand its structure and optimize for it. And these APIs complement the original RDD one. Actually, they're implemented on top of it. Basically, they're just kind of higher level APIs, but you can easily interoperate with code using RDDs as well. Okay, so what is structured? Why are we doing this? So structure, basically, it means to construct or arrange according to a plan, to give pattern or organization. So that's what we're trying to do to the data, as well as to a lot of the computations you put in it so that we can understand what they're doing. Why do we want to do this? By definition, structure will obviously limit what can be expressed because it makes things fit a particular plan. But in practice, we found that even using these structured APIs, you can actually capture a lot of the computations people really want to do on a cluster. And using features in Scala, for example, such as case classes and implicits and things like that, it's very lightweight for the user to use as well. So it's pretty easy to just use these the same way that the functional API worked. And basically limiting the space of what you can express enables optimizations. I'm going to spend a whole bunch of time talking about optimizations underneath the structured API. Okay. So DataFrames and Datasets are language integrated APIs for structured data. They're actually built on the Spark SQL engine. And Spark SQL, if you're not familiar with it, it's essentially kind of an analytical database engine. So it does a lot of the optimizations you'd see in an analytical database such as Teradata or Vertica or something like that. For example, it does column-oriented storage and processing. It does query planning, trying to optimize query plans and so on. So basically, these APIs benefit from the same kind of optimizations you'd get in a high-performance optimized database. But instead of writing SQL, you're writing Scala or Python or one of Spark's languages. Data frames are a dynamically typed API, and they're a common API for data science in things like R and Python. And data sets are a statically typed one that looks a lot like RDDs. So I'll talk about both of them. And all these components are pretty new. Spark SQL itself came out around 2 years ago, and data frames and data sets came out last year. But they're all things you can use in the latest Spark releases. So how do these things execute? So basically, at a high level, we're going to start with a query or like a computation. Could be SQL, data frames, or data sets. We don't really care. All of these get turned into a logical plan, which is a tree of operators, kind of database operators. And then we're going to optimize them. We're going to take in information about the data catalog as well of what's out there and create a physical plan that we can actually run. And then we're going to use code generation actually to generate just a program using RDDs that's specialized for sort of the data types and things that you're using in your computation. And finally, a final piece of this sort of Spark SQL and dataset ecosystem is the data source API. So basically all these APIs can work with a wide variety of data sources like Hadoop file system or Cassandra or JSON or stuff like that. And there's a common way to plug those in as well, which I'll talk about in a bit. So that's basically the picture. Very similar to kind of query planning in a database. Okay. So what is the DataFrame API? So DataFrames hold rows, which are, they're just kind of generic containers with a known schema. So all the rows in one data frame have the same schema, the same fields, and they offer relational operations, which means sort of database operations through a DSL. So basically through embedded sort of DSL. So here's kind of how you use them. So you could create, for example, a Hive context, which is something used to read data from Apache Hive. Using, you could use just SQL on it, or you could do Hive context.table users. But basically, you can create a data frame that expresses some subset of the data in there. And then you can do transformations on it. So for example, here I'm picking the users that live in Massachusetts. And this is kind of the DSL part. So there's a small set of operators you can use to create these expressions. And instead of getting back just a Scala function, which is a bunch of bytecode, we actually get back an abstract syntax tree for the expression. So we see you're looking for a field called state and users, and you're checking if it's equal to Massachusetts. So now we can actually understand what's happening in your expression and maybe do some more interesting optimizations underneath. And then you can do standard stuff like in Spark, you can count these users, you can group them and average them. Notice that here again, instead of just having some weird function after, we have an explicit API to do average. So we don't run into that problem of figuring out what you're trying to do with a list if you use this API. And if you don't like using the DSL to do these things, you can also always view them again as Scala objects. So in this case, I'm going to do a map, and rows are these containers of arbitrary type. So I have to get the fields of them as, using these special getter methods. So I can get the first element and turn it to uppercase, or do my complicated Scala stuff. But the nice thing is that a lot of the common stuff you do can be done in the DSL, and then the engine understands it quite a bit better. So that's kind of what it looks like. Why did we choose this particular API? DataFrames are actually a really popular concept for data science in languages like R and Python. In Python, the interface to them is called pandas. And so we said, okay, this is something people already know. We actually wanted to cover other languages anyway. So let's give them an abstraction they already know. But interestingly, Spark, I think, is the first DataFrame API to make it declarative, which means to do optimization underneath. So in Python and in R, if you use DataFrames, each of these steps is evaluated eagerly. So there's no chance to do optimization. Like when you do this, it actually creates a table with all the users in Massachusetts, and then it counts them and so on. Or when you do this, it actually has to group them into sequences first and then average them. In Spark's API, it doesn't compute them until you force the result, like until you print it or save it somewhere. So it can actually optimize it in a declarative way. Okay, so that's kind of why why we chose to do this. And then the other nice thing about doing this is it integrates well with other data science libraries, and it also gives us a common interchange format between the different languages that Spark supports. So in Spark itself, the ML library, for example, machine learning takes data frames as input and output now. So anything, whether it's R or Python or Scala, can call into MLlib and just pass in a data frame. And in Python and R, you can map these to the sort of local single node data frames in those languages, and then use the libraries that work on those. So it's really easy to integrate it with these things. Okay, all right. And so what do these structured APIs enable? So the first thing is more compact data representation. We know the schema of the elements. It's a bunch when you specify the schema, it's a bunch of data types that we understand, like strings and integers and stuff. And so we can decide how to store them. We don't have to deal with like, oh, is this a class that has lots of subclasses or weird pointers to itself or stuff like that. And in particular, we use a column-oriented compressed format whenever we store these things in memory. When we process them, we still turn them into individual row objects, although that's likely to change actually in like after 2.0. The second thing it enables is optimization across the operators. We can look in the operators, see the expressions they're doing, and do things like join reordering or predicate pushdown, moving a filter down the tree to do it as early as possible, and so on. Same things you'd get in a database. And then the final thing we get is a runtime code generation, where we can generate code that's tailored and specialized for the computation you're doing right now, and not have to deal with generics and iterators and all these kind of virtual function calls you get otherwise. So in terms of performance, here's like some, one really simple kind of word count like benchmark. We wrote it in Python and Scala using the RDD API, and there's like a difference. Python is definitely slower. And then we wrote it with DataFrames, and with DataFrames, this was slightly faster even than the Scala code, basically due to being specialized for this computation, due to having fewer kind of virtual calls. And also you get the same performance in every language that maps to it, because it's the same kind of query plan and execution engine underneath. So I'll talk a little more about performance later, but basically this is the kind of stuff we can do with it. Okay, so that was DataFrames. Now, if you're especially, if you're a Scala developer, you might, be kind of unsettled by this loosely typed nature of it, this like get string 0 and all that stuff. That seems dangerous. That might, if it compiles, it might not run. So that's pretty scary. But luckily, you can also do this as a typed API. So the Dataset API is trying to make it typed. Basically, with datasets, you're going to have a dataset of objects of a given class, and whenever you look at them in Scala, we're going to actually create objects of that class, and everything you write will be type safe. But underneath, a lot of the operations can still use the same data format and some of the same optimizations. Okay. So how does that work? So, let's just have a bunch of case classes. It actually, in Scala, it works primarily on case classes. In Java, it works on Java beans. So, you have some case classes with some fields. Here we've got users and messages each contain a user as well. So it can be some nested sort of data. So first thing you can do is you can read a data frame. This is untyped. So here we're reading a JSON file. And actually, Spark SQL looks at the JSON and infers a schema for it. And hopefully, in this case, we know that schema is going to match messages and users. And then you can do dataframe.asMessage and get back a data set of message. And if the JSON has the right fields, we're going to view this as a bunch of message objects. And now that you've got messages, you can do nice type-safe operations that act on the Scala types. So for example, you can filter out, messages whose text contains Spark, and you've just got a message object, and you look at its fields. This gives you a new data set of message. You can pull out the user from each message. This gives you a data set of user. And as long as you're using case classes in here, basically, the API kind of works, and you get back new data sets. So that's what that looks like. And if you want, you can also use the sort of less safe data frame methods as well, where you just pass in field names and stuff like that. So for example, let's do group by user.name, pass that in and count. This is actually, if you didn't want to do this, you could also pass in a function, like you could group by, underscore.user.name if you wanted to do that instead. But you can also go back to this one. Again, you get back, it keeps track of the Scala types. In this case, you don't have names for them anymore, but it's just a tuple of string and int. So that's basically how the API works. So you get a lot of the, the properties of the previous one, but you have types. Okay. So just a few details inside it. To let you plug in types and to make it actually work, datasets, each dataset comes with an implicit encoder object for its type T. So if you've got a dataset T and an encoder of T, you can build a data frame. And that maps back and forth between Scala objects and SQL rows, which are these generic containers that I talked about earlier. So you need that kind of object. We create them automatically for case classes, and it's not yet a public API to add your own, but it will probably be soon. We're just trying to iron out the details, to use it for a while before committing to a public API for these things, because it's important for these things to be high performance. So we want to play with a few different things. And basically, the encoder API itself is like, oh, given your object and a thing for like writing data into a row, like, go ahead and write it. That's what it looks like. The dataset methods take either closures or expressions in the DSL I described before. And then a final thing we want to do that will be cool to do, it's not, we haven't done it yet, is for some of the closures, we want to understand their semantics even if you pass in a closure. And that's possible now in Scala using features such as macros and metaprogramming. So for example, when you pass in like this kind of function here, m.user, we should be able, to know that you're just pulling out the user field, and we don't need to initialize like all the other fields in the message, right? If this was an arbitrary function, we'd have to read all the fields from the message and populate it, and then you only pull out the user, and we wasted time pulling out the string and stuff. But if we could analyze this function, we could just create a message object where only the user field is set, for example. So that's something we want to do in the future. There are some at least kind of research prototype type systems that do some of this, and we want to see if we can do it sort of for real in like sort of real user programs. But we're not using that yet. So there's still like a small kind of performance trade-off. If you use the DSL, we get slightly better performance. Okay, so that's how datasets work. And so long-term, RDDs will remain kind of the low-level API in Spark. If you know what you're doing, you have Java objects and you control their layout and their memory usage and so on, you can use it, and a lot of existing libraries use it. DataFrames and Datasets are a higher-level API with more semantics and optimizations. And our new libraries, the standard libraries, will increasingly use these as the interchange format. One really good reason for that is also to make it easy to pass data into these libraries from Python and R and so on. So we're already doing this with MLlib and with this thing called DataFrames, which is a new graph processing API based on DataFrames. And it's always, if you actually work with this, it's super easy to convert back and forth between the two as well. Okay, so that's kind of how we're trying to tackle these problems. Okay. So then next thing I want to talk about is some optimizations that these APIs enable, just to show what we're getting out of them, more than just putting up one graph once. And I'm going to talk about two of these. One is the data sources for reading stuff from external systems, and one is CPU and performance optimizations through code generation. Okay, so data sources are a common interface for both datasets and data frames and SQL actually to access external storage. And the really cool thing about it, I showed them a bit with JSON before, but the really cool thing is if you write a Spark application and you have your own types inside it, you can migrate it across very different storage systems like Hive or Cassandra or JSON files or Avo. You can start with a JSON file on your laptop, build your thing, and then run it in Cassandra. And then if you have the same field names and schema, the same program will work. So it's only that line at the beginning of a program that loads the data that has to change. The other thing that's cool about these is because we have these structured semantics after, we know which fields you're accessing and which parts of the data you use, we can also push down part of the query into data sources, which is not really possible in the original Spark. So in the original Spark, if you use the Cassandra API to read a table from Cassandra, you're going to get all the fields in it, or you have to jump through some hoops to tell it to only read some fields. But here, if you use data frames or datasets and we see your class only has 2 of the fields in it, we're only going to read those 2 fields, and we don't need to do a lot of extra wasted work. So internally, data sources can implement these different interfaces based on how smart they are, how much computation they can do. So some data sources just do a table scan. All they can do is read the whole data. You can't just like jump in the middle of it and pull stuff out. So CSV and JSON are examples. Some of them support a prune scan, which is just to read specific columns. These are columnar things like Cassandra and HBase. And some of them also support pushing filters into the data source itself and doing those, maybe somewhere else, not having to send back everything over the network. So things like JDBC when you connect to a database, and Parquet and Hive, which support indexing and pulling out just some parts of the data. So just as a simple example, I'm going to show this in SQL. You could have a data source for JSON, and you could do stuff like this, like select user.id and text, and it's going to read the whole JSON file. There's no nice way to parse JSON kind of incrementally. You could have something like JDBC, where you select, here you have these users, and you want to select age for users where language equals English. And you can also have some combination of them, and in the same system, combine these two different data sources. And when you do have these MySQL things, because MySQL supports filter pushdown, Spark is going to read the whole JSON file, but then it's going to push part of the query into MySQL. So it will tell MySQL, hey, I only want the ID and age for things where language equals English, and pull those out. And so you don't have to read back all the data. So this is a pretty powerful feature because big data is expensive to move around, and this lets you save a lot of the work of actually loading the data you don't care about. So this is kind of the data source API, and it benefits from the structure stuff shown before. Okay, cool. And then the second thing that we're trying to do under this API is CPU and memory optimization. And that has a lot to do with basically hardware trends. So when Spark kind of began in 2010, a lot of big data systems were bottlenecked on I/O. So back then, storage was mostly on hard disks, and one disk has around 50 megabytes per second bandwidth. You would probably have like a dozen disks in a server, but still, it's fairly limited. And networks in data centers were pretty small. Maybe you got 1 gigabit per second bandwidth, and CPUs were around 3 gigahertz. If you look now at the common configuration, like if you just launch a bunch of nodes on EC2, a lot of data, especially very recent kind of hot data, is placed on SSDs, and these can be a lot faster. Even one SSD can be around 10 times faster than a disk. Networks are pretty much everywhere in data centers. They've jumped to 10 gigabits, and there's also 40 gigabit, that will become pretty standard soon. But CPUs, unfortunately, are still around 3 gigahertz. And sure, there are a couple more cores, but not enough to make up for the difference compared to 5 years ago. So basically, these things improved by a factor of 10. The CPU didn't. So all of a sudden, back in 2010, the name of the game was just avoid I/O, definitely avoid network I/O whenever possible, maximize data locality, group data together to make it fast, and try to avoid disk I/O, which we did through caching hot data and memory. But now, even if you're going, with just basic data right off your SSD, you need to be really efficient in the CPU as well in order to get the maximum performance. So we have a set of different optimizations that try to do this, which together are called Project Tungsten. And basically, they do three main things. Runtime code generation, the specialized code I talked about, exploiting cache locality, and off-heap memory management, basically managing binary data instead of using Java objects and sort of their overhead. So Tungsten basically encodes rows of data, supporting in the kind of schemas that Spark can express as binary data in a much more compact way than Java objects. Obviously, it's less generic than Java objects because they don't have lots of pointers to each other and stuff like that. But it's pretty good if you have structured data. So if you have a row of elements like a number and two strings, it's going to encode them into a pretty small object, not tiny, but much easier to work with, which has like a bit set for which field is null, and then integers are just in binary form, and then strings are basically in this kind of binary data section at the end. And they're packed together. They're all kind of packed next to each other with no pointers. And in a lot of workloads, this basically leads to a lot of a save space, which is important both for like cache data that lives long term, and even for short-term data. You don't want to be allocating lots of memory to to group data or stuff like that. So this is like one really simple kind of benchmark that that shows that. Okay, so this is the first part, is the binary format. The second part is runtime code generation. So we start with an expression like in the DSL or in SQL, and then internally we view this as an AST. There's this thing called Catalyst, which is Spark SQL's query optimizer that can capture these things. And then finally we generate bytecode, or actually we generate Java code and then compile it that works with that. And one of the things with this is because we're storing the object in this binary format, we actually have the code work directly on binary data with pointers. So we use this platform.getInt, which is a JVM like intrinsic to work with pointers. It's part of sun.misc.onSafe. So this is kind of basically this allows the code to work with data, whether it's in the Java heap or outside of it. So we can just allocate a bunch of memory outside the heap and work with it and get similar performance to what you did if you did, like malloc in C, and then you had a bunch of structs in there and tried to read fields from them. Now, it may seem like a little scary to be doing this stuff in the JVM, but one of the nice things with Spark is that data has a very well-defined life cycle. It's pretty clear, like when you put something in the cache, when you remove it, and you can't really have pointers to it outside. Each time we pull out an object, we copy the fields into a Java object, so it's pretty easy to manage. If this was something with lots of data structures with pointers and chains and stuff like that, it would be a lot harder. But here, it's not too hard to manage a bunch of memory outside the heap to do this. And you get really good performance. You get similar performance to these things that were written, from the ground up to do that. So that's basically how this part works. So the long-term vision for this is basically we have a bunch of language front ends. They all create a logical plan. This part is mostly in there today. It works for all of them. And then we can map it to different backends. And right now, we're still executing the code in the JVM, but we're also interested in doing stuff like LLVM, so basically generating assembly code instead, or vector instructions, or even using other types of memory, like 3D crosspoint or memory mapping on SSD directly or stuff like that, so that we can work with new types of hardware. And it's pretty important because basically the future of hardware is going to be these these new storage devices and these new kind of computing units that the JVM doesn't run really well on. And we don't want to lose like the really nice things of working in Scala and Java in the user API. So we need to figure out a way to map it onto these pieces of hardware. Okay, so that's that part. Okay, and then the final part I'll talk about very briefly is kind of some of the next steps happening with this in Spark 2.0. So Spark 2.0 is the next major release of Spark. It will come out probably around the end of May, so it's coming up pretty soon, and it's got a lot of exciting features in it. Just to give you a sense of what it means, there's sort of Spark's versioning scheme. So in Spark, we just use semantic versioning. So major version, which 2.0 is, means that it may change APIs. A minor version, which most of our releases have been so far, it can add APIs and features, but it can't break backwards compatibility. Actually, we tried to enforce binary compatibility, so you don't even have to recompile your application. And patch versions can only have bug fixes, and they definitely can't break binary compatibility either. So 2.0 is sort of a chance to clean up and think about some of the major APIs. Now, in reality, we really hate breaking APIs. Anyone who's worked on the project early on knows that people such as myself, were extremely stubborn about not breaking APIs, because the worst thing as a developer is you update some library that is not your main type of work, and all of a sudden you have to work for like a few hours to just fix everything. And if you don't update it, you don't get bug fixes. If you do update it, you get all this junk that you didn't want to work with. So we really try not to break these APIs. And in Spark 2.0, we haven't done a lot of API breaking. The most thing we've done is we've tried to remove some dependencies that were causing conflicts. So like one kind of interesting story is we used Guava to implement the option type in Java, because we have some APIs involving options. And option seems like a really simple class, but somehow Guava broke API compatibility for option in one of its minor releases. So that's definitely unfortunate, because we were stuck with our public API with some Guava 1.5 or whatever old version of it is. So we've done a few things like that, but mostly things will work as before. Some may require recompiling, because we did change some of the type stuff in Scala, some of the type magic to make them to make a few things more uniform. Okay. And there are a whole bunch of big features in 2.0. There's a lot more of Tungsten, actually. A lot of the stuff I described, like the code generation, is improved quite a bit. There's a machine learning model export. And then the thing I want to talk about is a new structured API called structured streaming, which gives us the same kind of optimization I showed with DataFrames and Datasets, but on streaming computation. And I just have a couple of slides on it. I'm not going to spend a super long time. So structured streaming is actually an attempt to do, in fact, a bit more than streaming. It comes from seeing what people did with Spark streaming and with sort of other streaming engines. So real-time processing is obviously pretty important for a lot of applications. But what we found when people deploy Spark streaming or other systems is no one is just doing streaming. No one just says, yeah, I have a stream of objects and I just want to run a map over it, and yeah, I'm going to get another stream back. In fact, they usually combine it with batch or interactive queries. So for example, you might have a stream that tracks state and updates it in a database. Maybe it puts it in a MySQL database, or in some weird, in Redis, or some other, some fast in-memory database. And the whole point of doing the stream is because you have a web application in front that's going to run SQL queries on it. So that's a really common use case, but that's not streaming. It's not supported well by many streaming engines. Or another example is you train a machine learning model offline, which is a batch job, and then you update it or you apply it to a stream. So Spark is very well suited to do this, because the engine can actually support all these workloads, and we just want to make sure the APIs let you easily mix them as well. So structured streaming is a high-level streaming API built on DataFrames and Datasets. It's got a bunch of features that make streaming easy to work with, like event time support, so your data can come in any order, and we deal with late data and update results, windowing, sessionization, and data sources and sinks that are pretty powerful, similar to the ones I showed before. And it's optimized using Tungsten. But it's also designed to support batch and interactive queries. So for example, you can aggregate data using a stream and then serve it out of memory using JDBC and plug in your web application to Spark and just have a single consistent thing, no managing two weird systems that don't know how to talk to each other very well. You can change the queries at runtime if you have a new query. You can build and apply ML models. And we're working to make all of Spark's libraries tie in with this to let you combine them. So we're calling this, we wanted to give it a name because it's not just streaming. We're calling these applications that combine the mode continuous applications. So it's an entire end-to-end application, not just a map on a stream. So just as an example of things you can do with this, very common use case for streaming today is to do ETL, or extract, transform, and load. So maybe you start with a message bus like Kafka, and then you do ETL and you put stuff in a database. Or another common thing is reporting. You compute some aggregates and then you push it to some applications. So we're going to support these two things. These are kind of things that are pretty doable today. Another thing you may want to do, though, is ad hoc queries. And in structured streaming, you can just connect to the system using something like JDBC and just run queries on the state in the stream. So this is another type of processing. Previously, you would have had to find some kind of database and figure out how to consistently update it and do these queries. And another similar thing is a machine learning model. So this is kind of a closed loop where, like, as you learn stuff, you feed it back into the stream, and you need to keep iterating from the previous one. So basically, the goal is to support these end-to-end applications, so you write these things in a single API. So I'll give a really brief introduction to the structured streaming API. We thought a bunch about how to create this API, basically we decided that actually you already know it. You don't need to create a new API. So the model in the system has been that sort of the simplest way to think about streaming analytics is not having to think about the streaming aspect itself, how to actually do stuff incrementally. Just tell me what you want to get at the end, and we'll compute an incremental plan to do that computation. So basically, all you have to do is describe the final result you want. You don't have to say, like, oh yeah, when you get a record, update this state over there and send a message to that guy and do something else. The API is based on data frames. Basically, in Spark 1.x, we had these static fixed size data frames that were a table. In 2.0, we just represent streams as infinite data frames, essentially. So rows keep getting added at the end. And you have the same DataFrame API to specify what you want to get out of it. Basically, you tell us what you want at the end, and we do it incrementally as the data set grows because new records have been added into it. Okay, so just a really short example on it. Here's like a simple batch job using data frames. There's no streaming here. This is how you do a batch job. So here we're going to read, a JSON file and do a group by and figure out the average latency by user ID and hour. And then we're going to write it to MySQL. This is the data source, writing API. So that's a batch job. And we can run this once on a file. If we want to do streaming instead, we just change a couple of words in here. So we say, oh, instead of a fixed file, let's stream stuff from a directory. So every time a file is uploaded into that S3 bucket, we're going to update our result. So we just change that from read to stream. And here we're going to say, okay, let's start a stream to update MySQL with these results. And as results get read, as a file gets read from S3, we're going to run a transaction on MySQL to update the rows that change. So even if we get data that's late or things like that, like some record for a user ID comes in 3 hours ago, we can actually update the table. And the result is the same as if you had just run the batch job on all the latest data so far. So if you understand what the batch job does, you understand what the result of this is. So the way it executes is logically, you give us a data frame and you do operations as if you had all the data so far, like as if you had a giant table with all the data, and you tell us what you want to compute. We look at the plan, we say, okay, this is a thing we know how to do incrementally, and then we actually run it incrementally in a streaming fashion. So we track state and we actually execute it incrementally and save the result. And basically, to do this transformation, we basically transform the batch query plan that we had into a continuous one. And we use a lot of information about the structure of the data and of the operators to know that, oh, you're doing a group by this field, that means we need to maintain such and such state, or you're only reading these columns and so on. So for example, in the one I showed, the continuous plan will be, we're going to scan for new files in S3. When files come in, we're going to do a stateful aggregate. So we're going to have some state on the side with the count so far, and we're going to update them based on the new user IDs and records that came in. And then we're going to update MySQL each time new data comes in. Obviously, we can't do this for every computation. Some of them can't be done incrementally, but then we'll tell you about that. So for the ones that can be done incrementally, we'll automatically incrementalize them for you. Okay, so that's really a brief overview of structured streaming. Spark 2.0 will have the first version with a basic API focused on ETL. And in Spark 2.1, we're going to add a bunch of other sources and sinks and more complex kind of aggregations and things like machine learning. So it's under heavy development, but the first one will be out in hopefully in less than a month. Okay, and so in conclusion, basically getting high performance for big data is increasingly hard. It requires these low-level CPU and memory optimizations. In Spark, we're doing that while keeping the nice aspects of a Scala API through these type-safe DSLs. And we're still exploring some new ground here, but we're pretty happy so far. I mean, these are used by real users, and they basically work. There's stuff that can be improved a bit, but it's pretty cool that you're able to do this in Scala. And I think future things coming into Scala, such as new meta-programming features, will in fact make this even easier. And I'm super excited about the direction Scala is moving to facilitate really powerful APIs like this. One final thing, if you want to learn Spark, our company, Databricks, gives you a free online environment with a mini Spark cluster called Community Edition. And we have a whole bunch of video tutorials and interactive ones you can just type in and do. So I encourage you to check that out online. Thanks. Yeah, good question. Yeah, how do you do windowing in a stream? So windowing for us is just a group by. So basically, like here I grouped by some fields in the data. When you do windowing, you say, window it, say, by the hour field and have 10 hours or something like that. And you get keys, which are the window ID, and values, which are, well, basically each row in that window. So windowing is basically a group by. It's kind of like doing group by some function of hour, where the function can put each one into many time windows. Okay. Yeah, the APIs for this are online. Actually, I should have had a link, but if you Google for Spark structured streaming, there's an API doc that describes this. So I should have had a pointer to that.
Thank you.
Well,
yeah.
Do all your existing streaming sources work with this new 2.0 API?
Yeah,
Kafka?
Good question. So the existing ones don't all work yet. They need a bit of wrapping to make them work here. So I think the first release will likely not have Kafka, but then 2.1 will. Or we might even release, by we, I mean Databricks, might release Kafka as an external package even earlier on while we're developing it. We just didn't have time to finalize it for the release deadline. But we definitely intend to support all of these things. It just it has to be done kind of step by step. Yeah.
Back here.
Yeah.
I'm curious. Would it be possible to get 211 binaries on the website?
Oh yeah.
Rather than have to build it ourselves?
Yeah, that's a really good question. Yeah, we're going to do that by default starting in 2.0. In Spark 2.0, we'll put those as the default. And it might make sense to put binaries for all of them. I think it's mostly an issue of basically of CDN kind of space that's expensive. But I think it's a really good point. I think we should be doing that. Yeah. Yeah.
One last question.
Yeah. One question. Here?
Yeah. This new streaming API here.
Yeah.
What are the odds we're going to be able to plug in the reactive streams to non-spec into it?
Oh, good question. Plugging in the reactive streams. Yeah, we haven't looked into that too much, but I think that's a really good idea. We are designing it to have both sources and sinks that are pluggable and that support interesting semantics. Like when you have late records, we should be able to tell a sink that stuff is late, and you should have some way to know what to deal with that. So we haven't looked at it yet, but I think it would definitely be interesting to look at. Yeah. Okay, well, thanks a lot.